Welcome to another module in this massive open online course. We are looking at convolutional code. So, let us look at the matrix representation of a convolutional code. Okay. So, what we want to look at is the matrix. Matrix representation of a convolutional code, and what we have is we want to form the generator matrix. View it as a linear operation, form what is known as the generator matrix for this convolutional code. Now, consider the input bit sequence again, as usual. Remember, for any we have to start to get the coded bit sequence, we have to start with the input bit sequence, which let us say is x0, x1, x2. Okay, this is your input bit sequence. Now, this input bit sequence, let us write this as a row vector. Okay, so I am going to write this as x0, x1, okay. We are writing this as a row vector. Okay, this is your input bit sequence. Now, I want to multiply this by a matrix to generate the convolutional code. So, now you can see, let us say this column, the first column corresponds to C0. Now, we have x0, C0, remember C0, 0 is x0 plus x of 0 minus 2, that is x of minus 2. Now, if we set x of minus 1, x of minus 2 to 0, once again similar to what we have been setting, that is the previous bits before the starting of time at time t equal to 0, if we set those dummy bits to 0, what we have is rather, so we are setting x of minus 1 equals x of minus 2 equals 0. So, what we have is C0, 0 is simply x of 0 plus x of minus 2, but x of minus 2 is 0. So, this is simply x of 0. So, this is x of 0 into 1. Similarly, and of course, x of 1 does not enter the picture. So, it is going to be multiplied by 0, x of 2 also does not enter the picture, going to be multiplied, all the rest of the. So, this column corresponds to C0, 0. You can think of the rows as corresponding to the input information bits. For instance, this corresponds to x of 0, x of 1, x of 2, x of 3 and so on. Okay. Okay. Now, this corresponds to C of 0, C of 1 of 0, that is of course again, I am sorry, this corresponds to first row is x of 0, second row x of 1, x of 2, x of 3, x of 4 and so on. Okay. Now, C1 of 0 is naturally x0 into 1 plus x1 into x1 does not enter the picture. So, it is plus x0 plus x minus 1 plus x minus 2, x minus 1, x minus 2 are 0. So, this is simply x of 0 into 1 plus x of 1 into 0, x of 2 into 0 and so on. And therefore, now you have this block. Now, similarly, let us look at this for C0 of 1 and C 1 of 1. Now, C0 of 1 is simply x of 1 into 1. X of 0 does not enter the picture, so 0 plus x of minus 1, x of minus 1 is 0. C1 of 1 is x1 into 1 plus x0 into 1 plus x of minus 1, which is 0. Rest do not enter the picture, so they are zeros. Okay, so zeros and so on. And now similarly you have C0 of 2, C1 of 2. You can see C0 of 2 is x of 2 plus 0 times x of 1 plus 1 times x of 0. C1 of 2 is basically, this is you can see this is 1 times x of 2 plus 1 times x of 1 plus 1 times x of 0, rest x3, x4, etc. do not enter the picture. And you can see in every subsequent this block will shift by 1. You can see C0 of 3 and C1 of 3. C0 of 3 is x of 3 into 1, x of 2 into 0, x of 1 into 0, x of 1 into 1 plus rest all are 0, and C1 of 3 is x of 3 into 1 plus x of 2 into 1 plus x of 1 into 1, 0, rest all are 0. So, you can see that this block 1 0 1 1 1 1 is going to be shifted. So, this block is going to be shifted down by 1 row in every subsequent time instant. This block, we are talking about this block 1 0 1 1 1 1 is shifted downward by 1 in every time instant. Okay. For instance, if you can look at this, C0 of 3, let me just look at this entry C0 of 3. This corresponds to, now you can see C0 of 3 equals 1 times x of 3 plus 0 times x of 2 plus 1 times x of 1, which is equal to x of 3 plus x of 1. That is your code bit 0 at time 3. Code bit 0 at time 3. Okay, so this block 1 0 1 1 1 1 is shifted downward by 1 in every time instant, and this matrix is known as the generator matrix for this convolutional code. So, what I can do is I can take the input vector x bar, row vector, this is equal to G times, or basically this into the generator matrix G this is equal to C bar. Which is basically your output code word vector. Okay. So, I can represent this code generation as a linear transformation for the, this basically captures the generation of the convolutional code. Okay. Let us look at yet another representation of the convolutional code. This is known as a transform domain representation. Or let me just rewrite it clearly. Let us call this as the transform as the transform domain representation. And we can define the D transform of the code. So, we define what is known as the D transform. We define the D transform of the code as x of D equals, this is, or not the code, this is the D transform of the information bit sequence. So, this is j equal to 0 to infinity x of j d to the power of j. Now, observe that this is similar to the z transform. Remember, z transform is j equal to 0 to infinity x of j z to the power of minus j. This is your z transform, but this is not the z transform, this is the d transform, and this d transform is simply obtained by setting, you can see, obtained by setting d equal to so d basically represent, remember z inverse that simply represents a delay. So, d represents a delay element, right, correct. So, d, this quantity d simply represents a delay element. Remember, we might remember from the theory of z transform of digital signal processing, that is the z transform for a given sequence xn, the z transform is simply summation xn z to the power of minus n. We are replacing d by z inverse, so this becomes xn d to the power of n, or xj d to the power of j, and this is particularly convenient for representation of an information bit sequence, or for that matter also a coded bit sequence, alright. So, this is known as the D transform. So, D is equal to Z inverse, which represents the delay, okay. So, this system D characterizes the delay, okay. Now, again it goes without saying, for instance, I have x of j with transform x of D, I have x of j minus k, what is the corresponding transform. Now, of course, first let us start with this, x of j minus k starts from, so you have k equal to, or j equal to 0 to infinity, x of j minus k d to the power of k. Now, j minus k, x, if x starts only at 0, j equal to 0, x of j minus k only starts at j equal to k, because x of minus 1 and so on are 0. So, this starts at j equal to k to infinity x of j dj. This is since x of minus 1 etc. are 0. Now, substitute j minus k equal to j tilde implies j equals j tilde plus k. So, this becomes j tilde equal to 0 to infinity x of, well, I am sorry, this should be x of j minus k j tilde d to the power of j tilde plus k, and this you can clearly see is d to the power of k j tilde equal to 0 to infinity x of j tilde into d raised to j tilde, and this you can clearly see is x of d. So, this is simply d to the power of k into x of d. So, the transform of x j minus k is d to the power of k. Now in particular, if you look at this x of j minus 1, that is in particular if you look at x of j minus 1, that will have a transform d times x of d, and therefore this d represents a delay. That is what you can say, this d represents a delay of 1 unit. That is what you can see, d represents a delay of 1 time instant. D represents a delay of 1 time instant. Okay. Now let us go back to our convolutional code. Alright, let us now go back with this knowledge of D transform. Let us now go back to our convolutional code and let us try to develop a D domain representation of the convolutional code. So let us go back to our convolutional code. Now when you go back to our convolutional code, what you see is C naught of j is x of j plus x of j minus 2. If you take the D transform, what you are going to have is C naught of D is equal to x of D, D transform of this, plus D transform of x of j minus 2, that we already seen is D square times x of d. Okay, x of j minus k is d to the power of k times x of d, and therefore the D transform of C naught code bit sequence 0 is simply x of d into 1 plus d square. Okay, so we have an elegant D domain relation to characterize the D transform of the coded bit sequence 0. Similarly, C1 of j is equal to x of j plus x of j minus 1 plus x of j minus 2. If you take once again the D transform, C1 of d equals x of d plus d times x of j minus 1 has D transform d times x of d plus x of d minus j minus 2 d square times x of d. This is equal to x of d into 1 plus d plus d square. Okay, so this is the relation that we have. So finally, to summarize this, we can write in the D transform domain C0 of d equals x of d into 1 plus d square, C1 of d equals x of d into 1 plus d square. This can now be represented using a shift register architecture. So what we are now going to do is represent these using a shift register we can now represent this using a shift register architecture. I am going to use a shift register architecture to represent this convolutional code, which is convenient, and this shift register architecture was very popular, especially in the early days of the convolutional codes, to practically implement in a digital communication system, implement these convolutional codes in a digital communication system. In particular we can use a feed forward shift register architecture. Okay, I can use a feed forward. So a convolutional code So a convolutional code can be represented using a shift register architecture. In fact, below we are going to show a feed forward shift register architecture. A feed forward shift register architecture is given below. So remember, we have x of j, that is x of d. So we have x of j, it goes through a delay that gives rise to x of j minus 1. X of j minus 1 goes through another delay that gives rise to x of j minus 2. And what we can do now is basically, all I have to do is take this x of j, correct, x of j, we have x of j, and that gives me x of j plus x of j minus 2, that gives me x of j plus x of j minus 2. Let me draw this again for the sake of clarity. So I have x of j delay, that gives me x of j minus 1, delay, that gives me x of j minus 2. I take x of j, I add it to x of j minus 2, that gives me c0 of j. I take x of j, add x of j minus 1, and I also add to this x of j minus 2. So x of j plus x of j minus 1 plus x of j minus 2, that gives me c1j. Okay, so c0 j, this is equal to x of j plus x of j minus 2, c1 of j, this is equal to x of j plus x of j minus 1 plus x of j minus 2. So this is code bit 0, again it goes without saying, code bit 0 at time j, and this is your code bit 1, this is your code bit 1, at time j, and this is your feed forward shift register architecture. This is your feed forward shift register architecture. Okay. So what we have done in this module is basically we have looked at several things. We have first looked at a generator matrix representation of the convolutional code, or generation of a convolutional code based on a generator matrix. We have constructed the generator matrix. We have looked at the D domain formulation or D domain representation of any coded bit sequence, also the corresponding D domain representation of the filters, or basically the D domain representation of a convolutional code, and also this shift register architecture for generation of the convolutional code. That is the coded bit sequence given an information bit sequence. Alright, so we will stop here and look at other aspects in the subsequent modules, namely the more important and interesting aspects which are basically going to be extremely important. One is the state diagram representation of the convolutional code, followed by the extremely important and critical trellis diagram for the convolutional code, and the decoding, how to, now what we have seen so far is basically given the information bit sequence, how to generate the coded bit sequences. What we have to do now is consider the received sequence. Of course, the received sequence at the receiver might not be the same as the generated coded bit stream, because as we have said, the whole purpose of coding is because there can be errors over the channel. So now we have a received bit stream. From this, recover the corresponding coded bit stream. Of course, recover the corresponding information bit sequence. Of course, we said the information bit stream, ideally we would like to recover it without any errors, but in practice that is not possible, because the errors can only be made as low as possible, right? One can only target trying to make the error rate as low as possible. So trying to recover the maximal likelihood, alright, trying to recover the information bit sequence to the most accurate extent that is possible. That is going to be your aim. Look at the appropriate decoding process. That is the decoding principle, the maximum likelihood principle, and the corresponding Viterbi algorithm, which will be used for to reconstruct the information bit sequence from the received bit sequence. So we'll stop here. Thank you very much.